So we can define it in that way, that is by listing the members that are in the set. Then the second way is by describing the property or rule that connects its member. For example, M is equals to mathematical set. But mind you, the type of bracket that we make use of here is quite different from the normal parentheses that is being used. Then the next way of describing a set is by self-builder or theoretical notation. For example, A is equals to integer, that is x, such that x is less than 7. This means that the element of A is a set of integers x such that x is less than 7. Each member of a set is called an element of the set. Conventionally, capital letters A, B, C, X, Y, or any other letter are used to denote a set, while a small letter is being used, such as A, B, C, X, or Y, in small letter, are used to denote the elements of a set. For example, the set of all positive integers denoted by X, that is X, capital letter X stands for the set, while small letter X1, X2, X3, X subscript 1, X subscript 2, X subscript 3, that is small letter X, are elements of X, just as we are having here. That is, X is equals to the parenthesis of X subscript 1, small x subscript 1, small x subscript 2, small letter x subscript 3, and so on. Then we close the bracket. A symbol that looks like E but not E, capital letter E, means or implies is an element. And this is used to denote that a particular number or element belongs to a set. For example, if capital letter X is a set of all positive integers and small letter x is positive integer, then we can say that small letter x is a member of X, which is read as X is an element of X. If X, small letter x, is not a positive integer, now formerly we said capital letter X is a set of all positive integers. Now, if we now have a small letter x, which is not a positive integer, then we use the symbol that negates, which reads as not an element of, to describe x in relation to our capital letter X, that is our set X. Then we say X does not belong or is not a member of set X, which means that X is not an element of X. A set that has no element is called a null or empty set. When we say, and it is denoted by a circle or a 0 or O being crossed, just as we are having here, or an empty set, that is a set without any element. For example, N is equal to all Nigerians who are 300 years old, which is empty. I don't know if you've ever seen, or your great-grandpa, or you've ever heard of somebody that is 300 years of age. That is just an empty set. If you should conduct a census in Nigeria, it's not possible for us to have somebody that is 300 years of age. Now, a set whose number or element is finite is called a finite set. If the number of elements in a set is not finite, then the set is called infinite set. For example, M is equal to Y, such that Y is a whole number. 7 is less than Y, or 7 is less than or equals to Y, or Y is less than or equals to 10. It's a finite set because it is being, it has boundary. That is, it is countable. Finite set because the number of whole numbers between 7 and 29 is inclusive, unlimited, or countable. That is, we can count the numbers in between 7 and 29. It starts from 7 and ends with 29. But if it doesn't end with 29, then we say it is an infinite. Just we can see in example number B, which is Z is equal to X, such that X is a positive integer, When we say positive integer, we can start counting from 1 and keep counting even up to million, to billion, to trillion, and then you keep counting. It's an infinite set because the number of positive integer is unlimited. It is unlimited. That is, you can just keep counting, and then you keep counting till tomorrow, even so till you leave this planet Earth. Operations of sets. That is a subtopic under set. Subsets, and the first operation we'll be dealing with is subset and superset. The set A is a subset of set B if and only if every element of A is an element of B, and this is denoted by A subset B, where the C means subset of. That is, the symbol being used means subset of. If the set A contains some but not all the elements of set B, then A is said to be a proper subset of B, which is written as A subset B, and B is called a superset of A, denoted by B superset A. Note, that is something for us to note. Each set is a subset of itself. A mathematical set is a subset of a mathematical set. You can always find a mathematical set in a mathematical set. That is, we say that positive integer. Example of a positive integer will always be a subset of a positive integer. An empty set is a subset of every set. Then we'll go to universal set. The set of all the objects of specific interest from which other sets of a particular interest are drawn is called universal set. That is, a universal set contains all other sets. A set that contains only one element is called a unit set or singleton. For example, if U, capital letter U, equals all whole numbers, E is equal to all even numbers, D is equal to all odd numbers, P is equal to all prime numbers, X is equal to all prime numbers that are even. Mind you, we said all prime numbers that are even determine the universal set and unit sets. U is a universal set because U contains all the other elements of E, D, P, and X. Even numbers are whole numbers, odd numbers are whole numbers, prime numbers are whole numbers, and prime numbers that are not even also are whole numbers. Then we can easily say that since we can find E, D, P, and X in U, then U is our universal set, while E, D, P, and X are subsets of U, and U is a superset. Then X, mind you, X is all prime numbers that are even. And for us to have prime number that is even, that is only 2. X is a unit set because 2 is the only even prime number, and which makes it a singleton set or a unit set. That is, it's a unit set or singleton. Then we'll now go to another operations of sets, which is equality and difference of sets. Two sets, X and Y, are said to be equal if and only if every element of X is also an element of Y. That is, every element of X is found in Y, and every element in Y is also an element in X, which is denoted by X is equals to Y. That is, when all the elements that are found in set X are also the number of elements that is are the same type of element that we can find in Y without exemption, without addition, then we can easily say that our X, set X, is equals to set Y. Also, the difference of two sets, X minus Y, is a set of elements in X but not in Y. For example, if set X is equals to 2, 3, 4, 6, 10, and 12, and Y is equals to 10, 4, 3, 2, 12, and 6. Then X is equals to Y. Why? Why do you say that X is equals to Y? What happened in X and Y is just that it's been the way the pattern in which they are being arranged is quite different. But the elements that are in X are the same elements that are found in set Y. Because every element in X is also in Y, and every element in Y is also in X. Then our next example is example B. If X is equals to 2, 4, 6, 8, 10, 12, and 14, and Y is equals to 3, 4, 8, and 12, then X minus Y is a set of 2, 6, 10, and 14, which are elements in X that are not in Y. Also, Y minus X is the set of 6, that is, we only have 6, which is a unit set or singleton, which is the element in Y but not in X. Another operation of set a complement of set. That is, given that A is a complement of U, then the set of elements in U that are not in A form the subset of U. That is, this subset is called the complement of subsets, of the subset of A in U. This is denoted by A apostrophe, or you can just say A and put a C